Wow, there's a lot of you. This is pretty great. Well, let's see. I'm here to. My phone is not cooperating. Hang on a second. I wrote some notes down. Let's see. Okay, yes. Well, it is a great honor. My job here is to introduce Raf Andrea. That's a great honor. And let's see, what to tell you about Raf. I mean, most of you already know, but some of you don't. Raf has created or revolutionized several different areas in robotics. And that's not an exaggeration. That is not hype. I'm going to give you one example which affected me personally, which is that about 10 years ago, a guy came to me, Tom Wagner, and said, hey, I'm going to start a company and we're going to do warehouse robotics. And my instant reaction to that was, why bother Raf Andrea with Kiva Systems? They've already solved that problem. So in my mind, he created, founded, revolutionized warehouse robotics. And my reaction to Tom's statement was rather naive, but my understanding of the role of Kiva Systems, I think, has been borne out over time. It was purchased by Amazon and is still rolling and doing great stuff. So that's just one. I don't know what Raf is going to talk about, but I think you're going to see more here. So now there's much more to say. I'm not going to waste our time by giving you a long list of awards and distinctions that he has won. Instead, I think we want to hear Raf, and therefore, please join me in welcoming to the stage Raf Andrea.
Great to be here. I flew in last night. It was a long flight. I was pretty tired. I was still recovering from Eurovision, the final. It was a lot of fun. And I got in late, but early enough that I could still go and register. So I'm lining up in the registration, and I'm sitting with some folks and decide to do some small talk. And I'm sitting there for 3 or 4 minutes, and then I'm realizing the vibe is different than what I remember. I haven't been here in a long time. So I'm sitting there talking to people, and then a couple of minutes later, I realized I'm not lining up for ICRA, I'm lining up for MomoCon. I'm not making this up. And then I thought, why did it take me so long to figure out that I'm at the wrong lineup? And I think part of it was the crowd is different, but it's not that different, right? People in robotics have that playful nature. So it was a fun reminder of that. Okay, the clockwork universe. Nice depiction of it. It's a grand machine whose whole history, forwards and backwards in time, is dictated by initial conditions and the laws of physics. When I was a small boy, that was my view of the world. And in fact, it still is today, modified accordingly to take into account things like chaos, decidability, and the multiverse. This notion of determinism, the laws of physics dictating what should happen. I received my PhD in 1997. That was the same year that the first Harry Potter book came out, when Hong Kong became Chinese, and when Sojourner landed on Mars and explored its surface for the first time. So a long time ago. What I took out of my PhD, one of the main things that I took out was an appreciation for the science and the art of designing feedback systems, and especially with using first principles models as the backbone. So here's an example of this. And this is about as anti-black box as you could possibly get. So you're given a system, sigma sub p, governed by differential and algebraic equations, and its variables are split into 4 parts. D is the rest of the world. It's how the rest of the world affects the system. Z is the difference between the behavior that you want of the system and how it actually behaves. So these are the things that you want to keep small. C are the control variables. Ultimately, you have to design a system that acts on C that makes it behave like you want it to. You want Z to be as small as possible. And L are just modeling variables, also known as latent variables. And here's an example of this. It's a simple 1D suspension design. M is the sprung mass. You're sitting on the car. That's you. The bottom is a tire model, has a spring and a damper. And our job is to design this thing in the middle here, which is a relationship between x minus y, the difference between you and the wheel, and the forces that are produced, whereby Newton's laws, for every action there's a reaction. You see Fc appearing twice. And the control variables here are Fc and x minus y. The things you want to keep small are the difference between you on the top of the car and the road, but also the jerk, which is a measure of comfort. And D is the road, okay? And L are the latent variables. So it turns out that these types of problems, you could actually solve them by leveraging tools from H-infinity controls. And you can write a solution. Basically, you have to solve for those red things. People came up with some very nice tractable solutions for this, including my PhD advisor, John Doyle. And the thing that it spits out is a differential equation for your control systems, which turns out to be a spring, a damper, and an active system, all in one. It gives you all of this. Okay? So this was very illuminating to me, that you could design systems, and there's no parameters here that you have to identify. Everything is white box. It's like the extreme of anti-black box. Okay, so after I got my PhD, I joined the faculty at Cornell University, and I wanted to learn about robotics. I'd done a lot of control systems, but I've never really done robotics. So what better way to learn something than to teach it? So along with some colleagues, we founded the systems engineering program at Cornell University, and I decided to run a large program centered around RoboCup, the competition that had only been 3 years in existence at that time. So we introduced some innovations in the team. We had roughly 30 students every year, computer science, mechanical engineering, electrical engineering, undergrads and grads. And we came up with some innovations, including dribbling mechanisms so that you could actually control the ball, and omnidirectional drives so that you could actually move to intercept passes. We also co-introduced kicking with the Foo Fighters from Berlin. Now, when folks watched our videos and when we competed, naturally they think, well, Cornell did great because of good engineering. And that's certainly true. Cornell students are phenomenal. And also because of these innovations that we introduced. But the fact is everybody copied them the following year. If I were to say there's one thing that really allowed us to be successful, was actually our motion control. Our ability to make our robots do exactly what we wanted them to do, and to do it extremely quickly. So here's an example of this. The motion control for our robots. We first had an inner loop, which would make the dynamics of the system look like what you saw at the top, with the normalized inputs U sub I being in a certain range. We then looked at the envelope of all things that you could do, and we built a smaller envelope that allowed us to basically tractably create trajectories. And in doing so, we traded off performance for tractability. We came up with algorithms that could generate trajectories thousands of times faster than optimal, while sacrificing a very small amount of optimality. Here you see the number. We did some studies. 85% of the trajectories were within 82% of optimal. This was critical because it allowed us to create trajectories that were feasible by design, and it allowed us to explore what-if scenarios to build our strategy on top of that. And obviously, models are central to doing this. Matt already talked a little bit about Kiva. So you know about Kiva, you know about Amazon Robotics. There's, what I've heard is roughly 750,000 of these mobile robots running around warehouse facilities. There's probably at least 100,000 more running around other facilities with other mobile robots. So this problem of moving goods around in distribution facilities has really taken off. So what were some of the challenges in doing Kiva? At this conference 22 years ago, this paper came out. We made absolutely sure that our investors did not have a look at this paper when we started Kiva, which was right around the same time. Basically, you can read the highlighted parts. The bottom line was that the mean time between failure in mobile robots was 8 hours. And naturally, you would think that's because of the hardware. No, the control systems was a big part of this failures as well. Bottom line is that if you had, according to these statistics, if you had 1,000 mobile robots running around 24/7, you would expect roughly 1,000, and with perfect hardware, you would expect roughly 1,000 of them to break down every day. So clearly, we had a big challenge ahead of us to do something like Kiva. We had to make the system much, much more reliable. So I'm going to tell you a little bit about how we did that. So the underlying philosophy in the system architecture that I created was something that I got teased a lot about by the other two founders, Mick and Pete, and especially Mick. So much so that he took a sign that was lying around the floor of this very kind of shady facility that we were able to rent on the cheap to do our design, and he flipped it around the back and he wrote something and he put it outside of my office. And this is what he put. I still have this, right? So basically, I was focused on, look, if we're going to make the system reliable, we got to know exactly how this thing is going to operate. So let's start at the high level. How do you, assuming that we can make robots that can control themselves perfectly, how do you manage and coordinate them using tractable algorithms in the presence of network outages, making sure that you don't sacrifice much performance? And this is the result. When you see this video here, focus on the brown one. Drive unit is trying to go to the blue part, and as soon as it gets there, we pick a new random position. All the other drive units are doing the same. So being able to do this at scale, algorithms that would scale to thousands of mobile robots was really key. And this led to some very key patents that we obtained for the system. So this is the outer part. It assumes that the robots can do whatever they do perfectly well. How about the robots themselves? The philosophy here was, because these things, again, we wanted to have thousands of them, philosophy, these things had to be super inexpensive, but super reliable. So how do you do this? You want to use rugged, inexpensive actuators, clever mechanical design. The way we picked things up is we had a counter-rotating screw, only 3 actuators, and this is how we were able to pick up pods. These things weighed as little as 0 pounds, as much as 1,000 pounds, with the center of mass being in a huge range. It was okay for us to shift all of the complexity to the algorithms.
You guys are overloading it. So this is at least 1,200 pounds, right?
Yep. 1,200 to 1,300.
Wow. Actually, can one of you guys jump off?
Yeah. We'll have time for something on your side.
How's it doing?
Feels no different.
Whoa, why you being a wheelie there?
Okay, so there it popped a wheelie. That's Patrick and Eric, former RoboCup students who had joined Kiva at early days. They've done great things since that time. Very scientific testing, right? Okay, so how do we get this reliability? How do we get these robots to do what they were supposed to do? The key enabler here to get that level of reliability was learning and adaptation. Each robot was learning over 30 parameters. I can't get into the details of what exactly they were learning. Some of these things were pretty much fixed parameters to take into account manufacturing tolerances. Other things reflected wear and tear. Other things were things that could change relatively quickly. On top of that, these things had to also identify navigation parameters that were joint with the other robots. So this was like a huge consensus problem. And we came up with algorithms that provably would converge. And this is why we were comfortable deploying thousands of these robots that would drive straight over time and wouldn't crash into each other. Here you see a little video of what would happen when we took a robot out of manufacturing. It would not drive very straight at the beginning. You can see the time there. And after roughly about an hour of practicing lifting different pods up, it would drive extremely straight, and then it was ready to be shipped out to the warehouses where it could continue to learn and adapt and coexist with its fellow robots. Okay, so now for something completely different. I've been playing this game since I was a little kid. It's a mesmerizing game. I'm half decent at it. I can do it now in roughly a minute after I've practiced for about 10, 20 minutes to learn the little subtleties of the board and refresh my memory how to play it. Now, I've been obsessed with this game because I always wanted to create a machine that could do this. And over the last 7 or 8 years, I really wanted to see if these black box techniques, reinforcement learning in particular, how do they compare to do this job relative to model-based techniques. And a brilliant PhD student, Thomas Beath, several years ago, took up the challenge. And this was the result. We published this at ICRA last year, where we used reinforcement learning to actually solve the labyrinth maze. And this was the result.
After practicing for 6 hours, Cyberrunner is able to complete the maze faster than any previously recorded time.
So this was mesmerizing to me. When Thomas showed it to me for the first time, it was like, oh my God, this is amazing. We've since gotten that down to about an hour and a half. I'm pretty confident we can get this down to minutes with the right architectures for learning. We're so excited about this that we've open sourced it, and for a couple of $100, you can have one of these. We've given workshops at high schools. Everybody should have one of these. It's such an amazing, inexpensive test bed to do learning. And you could use classical techniques, you could use MPC, or you could use reinforcement learning. The biggest cost is the camera, and we can replace that with your mobile phone. And in fact, instead of having an external laptop with a GPU, pretty soon we'll be able to run all these algorithms on a mobile phone itself. So for less than $100, you can have this state-of-the-art platform. I really think that every high school should have one of these, and it's open source, it's free. Go to the website, and we're happy if you join the movement here. So this was a huge learning experience. I knew that these techniques could do well, but I was surprised at how well they did. And so I started asking myself, why does it do so well where model-based techniques, which we've tried, didn't really work so well? And for that, I go back to my PhD days, where there was this dogma in certainly my circle, I would say in the control community in general, which was that synthesis is harder than analysis. Analyzing whether a control system gives you a certain performance, what you see on the left here, is easier than designing a control system such that the system gives you a verifiable level of performance. And there was a good reason for this dogma. Because the synthesis was based on analysis, whereas the analysis techniques could generally be turned into a convex problem. For the synthesis problem, because you had to design a controller such that those analysis techniques were satisfied, it was not a convex problem. So there was this dogma that designing a control system was harder than analyzing it. But it is dogma, because a lot of times, you don't actually have to know what the consequences of your actions are going to be to know which is the better action. And I think this is the key of why something like reinforcement learning does so much better on a platform such as Cyberrunner than model-based control design. Cyberrunner doesn't have that many states, roughly a dozen, depends on how you count, but it does have some weird aspects to it. It has hysteresis, it has stiction and other sources of friction, which are notoriously very difficult to model using first principles. So if you try to come up with a first principle model of Cyberrunner, you get a mess, especially with hysteresis. The problem with model-based control design is that it tends to inherit the complexity of the model that you're working with, which is why people like reduced order models when you do control design. But for things like hysteresis and stiction, you really can't, you need that, otherwise you're throwing the baby out with the bathwater. So bottom line is the Achilles heel of model-based control design, even though it does all of these wonderful things that I showed you earlier, is that its complexity is dictated by the model, the complexity of the model. Whereas for reinforcement learning, if the strategy, it's really good at discovering strategies that are inherently simple, even though the underlying model may be arbitrarily complex. So what's my bottom line, what's my take here? Is that if you can use first principle models, you should. It allows you to do wonderful things like I showed you in the first part of my talk. The second is that, frankly, performance is overrated. And reliability and robustness is underrated. We like showing high performance things, but if you really think about it, where does high performance really, really matter? It matters in games, it matters in competition, and it matters in war. If you want to create a robotics company, no one's going to care if you leave 10% of performance on the table if you buy yourself a lot of robustness. So I think one of the things that I would like to maybe convey to the audience here is that let's focus less on performance and focus more on robustness and reliability, because that's really what has a lot of impact. My third point is that, for me, reinforcement learning is yet another tool in the arsenal. It's a very powerful tool. We've seen it do amazing things, but not everything should be reinforcement learning. Okay, now I'm going to switch for something completely different again to show you how models can be used in very different ways. This monstrosity that you see here on the left is the Cornell autonomous flying vehicle, which we built in 2000. It was huge. You can see it compared to the little drone that you see on the right. Here you see it flying. It was a scary thing. Each motor was 1,000 watts, so like more than a horsepower. The inertial unit was 1 liter in volume. And we bought riot shields so that we could, do research on it, because we were afraid of this thing. We eventually even got this thing to do a flip. So this was kind of like the state of the art with autonomous flying vehicles around the year 2000. Now, fortunately, I put all of that on hold to do Kiva. So by the time I went back into academia, I joined ETH Zurich. The core technology that you really need to do drones had advanced tremendously. And in particular, I would say batteries, motors, inertial navigation units, and compute power. So all of these had tremendous improvement in that roughly 10-year period. So we were able to do these wonderful things at the Flying Machine Arena at ETH Zurich. So we built rope bridges with drones. These are rope bridges that people actually walked on. The distributed flight array, modular vehicle design that would fly with an arbitrary number of elements, monospinner, simplest flying vehicle with one moving part, self-explanatory. Omnicopter, again, self-explanatory. Very classical control design, balance a pole, not so classical, see if you can throw it and catch it. We built a 6-meter tall tower with 1,500 brick modules with collaboration with Swiss architects Gramazzi and Kohler in front of a live audience at the Frac Center in France. This was in 2013. We did a couple of TED Talks. Here we showed our Skynet of 3 drones cooperating to throw a ball. And the second TED Talk that we did, we were flying vehicles over the audience. This is where we flew our tail sitter. It's a very, very stressful experience. Flying things over, hey, it's flying over Bill Gates. It's flying over Larry Page. Let's hope it doesn't crash into them. Okay, so models played a huge part in what we did. I'm going to show you one particular research that we did. It was led by my PhD student, Marcus Henn. I'll say a little bit more about him in a minute. So, of course, we used first principles models, and we also used adaptation like Kiva, but different than Kiva, the adaptation here didn't have to be parametric. Here the objective is for this vehicle to follow this virtual red dot in this figure 8. And after about 30 laps, it was able to learn how to do that. We then transfer that knowledge to being able to do the lap a little bit faster. So how do you take the knowledge that you learn in one regime and apply it to a slightly different regime? So we were able to make this thing progressively go faster and faster and faster until we were basically at the limits of the capabilities of this flying vehicle. So here it's going almost 100% full out, and it's following this trajectory perfectly well. So we really wanted to test the robustness of these algorithms, so we said, hey, let's do that again, but now let's have it balance a pole at the same time. So here, see Marcus put the pole back on the drone, gives it a little push, and when you start off, it does super, super poorly, but of course, over time, over practice, it learns how to compensate, and it does a pretty good job of balancing the pole while at the same time doing that figure 8. So we did a lot of fun things with the Flying Machine Arena. One of the things that we always did was do live demonstrations. It was a way for me to make sure that the students, PhD students, master students, undergrads, were really focusing on the important parts of the problem. If you're going to do a demo, it should work. You know, you've all heard of the demo effect. There is no such thing as the demo effect. All there is crappy system, crappy software. Okay? There's no reason why a system should not work when you're demonstrating it to people. It's just you didn't properly prepare. So we did Google I/O, we did Hanover Messe, and I already talked about that. One of the nice things that you can do with first principles models that you really can't do any other way is to explore things that you can do that are fundamental. For example, by analyzing the dynamics of a quad rotor, we discovered that it was actually possible to fly these things with less than 4 motors and propellers. In fact, with one, as you saw in the video. And here you see it being demonstrated for the BBC, where Flavio takes a big stick and shoves it into one of the motors. This was key in a collaboration that Verity, which is a startup that came out of my lab in 2014, did with Cirque du Soleil, where we did 400 shows on Broadway, where lampshades took off in the middle of the show, and did this wonderful choreographed performance with the actors here. And this was operated by, we weren't there, right? So they're called carpenters. That's the folks on Broadway that operate the system. They would operate the system, press the button, it would fly, and they would fly backstage, and the show was done. We actually had a fail-safe event, but with about 10 shows to go, the audience didn't even know. They thought it was part of the show that this thing blinked and went to the side. You will never see that, at least in my lifetime, you're not going to see these flying lawnmowers over people's heads in a show. It's amazing that we did it. It's kind of risks that you take as a startup. Risks, we were pretty confident of our technology. It's amazing that Cirque du Soleil took that risk with us. They probably didn't know. Okay? It's amazing that it all worked out. Okay, so Verity went on to do a lot of high-profile things that you may have heard and seen about. We ended up working with a lot of the top brands in entertainment. You see the folks here like Justin Bieber and Drake, etc., because we were known as the folks to go to when failure was not an option, when the system needed to work. Here we have a short video showing you some of the things that we've done. These are our Lucies. They're very small drones. They only weigh 50 grams. And this is mainly what we do with live events. Here you see our new spotlights that we've developed. These things use ultra-wideband to localize. Here you see Celine Dion. We tend to do a lot of touring shows. Michael Jackson just went live in Las Vegas. We also do one-time events. Lucy in the Sky was a dance troupe from Australia, where they actually created a whole show around our Lucy, called it Lucy in the Sky. And we put garbage bags on our drones, and we did this wonderful performance in 2047 Apolog, and we just finished the Eurovision contest, where we did 3 segments, including one with Nemo flying over the audience. While we were doing this very visible stuff, we were also doing something else behind the scenes. Now, that sign says confidential. That was because that was in October 2016. It's not confidential anymore. This is a very, very large warehouse in the United States, and we were doing this at the same time that we were doing Paramour on Broadway. What we were exploring here is the use of drones in indoor spaces to do inventory. So the idea was pretty straightforward. We slapped on some GoPros on our drones, and we had them execute missions, collect data, extract barcodes, and see how hard it would be to actually do this. We realized very quickly after we did this demonstrator that there was no way that we were going to be able to do this with this technology, with this approach. So we went into kind of stealth mode and created a system which we launched in 2021. So this is what Verity does today. I'm going to be quiet because there's a little bit of video with this. There's a sound with this video. Okay, so how does the system work? And I'll tell you a little bit about the role of models and how we do this in a minute. So our system is, the way we describe it is proven in the wild full level 5 autonomy. We're a cloud-based solution. The cloud interfaces with our client's warehouse management system and monitors its activity. Based on that information, it figures out what missions the drones should execute, what tasks they need to do. Those tasks are sent to the drones, who then figure out how to execute them. They do this fully autonomously: takeoff, landing, charging, obstacle avoidance, obstacle detection, route planning. Everything is done fully autonomously. They collect all of this data when they fly, various types of data, 2D, 3D depth. We also have RFID reading capabilities. Then they go back on the chargers and they pre-process all this data they collected. Then they upload their findings to the cloud. The cloud aggregates all of this data across one site, across multiple sites, and then interfaces back with the client's warehouse management system and also to people, and informs them on things that they should be doing to improve their operation. You don't need to touch these drones. The only time you need to touch them is after 3 to 6 months, the batteries wear out, because after cycling about 1,000, 1,500 times, you have to pop the old one out, put the new one in. It takes less than a minute for one of the warehouse workers to do this. So how do models and data fit into what we've been able to do? Okay? Data is super important here. Not only is Verity a company that is a mobile intelligence company, we're not moving stuff around like Kiva was. We're really just collecting data. So we use data to improve our system and to provide more value to our clients. So this is how we use data. We have over 2 million flights. We log every single flight and we learn from it. We have over 100 million scans, whether it's visual, whether it's RFID, where we collect data about the environment. We also monitor inventory movements. So we can figure out what is most likely to cause errors based on all of this historical information that we've obtained. We're operating in over 150 warehouses. It will be roughly 200 by the end of this year. And we've also uncovered a whole bunch of errors, and that is over 3 million. And that information allows you to figure out how to improve your client's operation. So let's look at each one of them one by one. So we founded Verity in 2014, our first generation system based on ultra-wideband, indoor ultra-wideband GPS system, the first hyperbolic ultra-wideband system, which meant that just by listening to ultra-wideband traffic, you could have an arbitrary number of entities that could figure out where they are. Just like GPS works outside, we did this for indoors. This is what our live events still uses. Although it had fixed missions, the flight was autonomous, but it wasn't autonomous operation. Mean time between failure was roughly every 2,000 flights. And the normalized cost, I'll say what that's normalized, what that means later. And you see the number of patents. Now, we used all of that data that we collected so that we could train our next generation system, which we launched in 2021. This is that stealth mode, when we did our first installations at ICRA and DSV. We moved to pure inside out, although we used all of that data set that we had before, but we still made use of passive reflectors that we randomly put into space to make sure that we had enough features that we could localize with. All missions are dynamic, and the operation is fully autonomous, like I just said a little while ago. Mean time between failure went up by a factor of 10, 25,000 flights, and the normalized cost went down by about a factor of 10. We'll soon be launching our third generation system, which has been trained with all of the data from our second generation system. Again, we're running in over 100 facilities. We're using all of this data to improve our system. So now we don't need these passive reflectors anymore. We have enough data, and we've made our algorithms robust enough that we can fly without these passive reflectors. The mean time between failure now is going to be up to 150,000 flights. Notice that the cost has only gone down by a factor of 2. Right? We're into the diminishing returns part of the exercise, but it's still a significant amount. Okay? Now, why 3? Why didn't I use normalized cost of 1 here? There's a next generation that we are working on, which is actually mainly software. The hardware is of course, we're going to improve it all the time. It's going to get our cost down to $1, normalized cost, so you can compare the various costs. We call it Swarm in a Box. The vision here is that we no longer have to go on site to commission a system. We can, just like a consumer product, when you buy a phone, you wrap it out of the box and it's ready to be used. We want to create a system where our clients, where we ship them a small crate, they take all the hardware, there's not much of it, they install it, and then the system commissions itself. This is where we will be in another 2 to 3 years. So this is how we use data. Okay, now, what can you do with all of this data that you collect from all of these facilities? One of our clients really wants to use our system for inspection. So they, instead of them doing the inspection by walking around, taking pictures and doing it manually, they're happy if we take a whole bunch of pictures and let them do the inspection based on the pictures that we take. One of the wonderful things about this is that they're doing labeling for us, right? These are rare events, okay? There's not that many anomalies, right? So it's great. We have human beings that are labeling data for us of rare events, and we're combining that with all of the other data that we collect so that we can train our system to recognize these anomalies. Okay? So again, we're monitoring the operation of all these systems. We become very good at determining where the issues are. The inputs that we feed our system, we're getting very good at figuring out what to focus in on so that we can have a higher probability of figuring out where the issues are. So you can see in this graph, if you just do this in a blind sort of way, where you uniformly scan the warehouse for problems, you're going to be on the linear curve. But by using all this prior experience that we've collected across all these multiple warehouses, we've gotten very good at figuring out where the errors are going to be. One of the other nice things is by monitoring where the warehouse management system, its knowledge of where things move, and augmenting that with information from our mobile updates, we can create a so-called digital twin, which is a representation of how the warehouse is working. And based on that digital twin, we can infer what issues are most likely to cause a disruption, which is great because then people can focus on those problems. But not only that, we can also figure out root causes. And we make those root causes available to our clients where they can fix the underlying problem. And again, this is extremely powerful for our clients. How are models used in doing all of this? Okay? Obviously, there were models used to make the first generation system drones fly. We still make extensive use of models, but all those models have been augmented by real world data. You can really only do this if you have huge amounts of data, which we now fortunately have. Now, could you try to do this without, using, is it black box? Not really. We still have very strong priors, which we use physical models for, including information like, mission planning and everything else. Not everything is a black box. But the point being here is that this is a combination of using first principles model and really using the data to inform the types of models that we want to have for our system. The ultimate goal is to have a purely digital representation of the physical world, a digital twin, where our clients can use as a tool to optimize their operations. They can explore what-if scenarios. What if we do things this way? What's going to happen? Okay? In order for them to do that, they need a digital twin, a model that is continuously kept up to date. And part of that model will be deterministic based on first principles models, but other big part of it will be simply dictated on data where we fit activity based on what we observe. And with that, I'm happy to stop and take any questions you may have.
As a courtesy to our presenters, please be mindful as you exit during Q&A.
Yeah, I will. So, thanks, Raph. I promised you guys something amazing, so that was amazing. Thanks very much. We do have time for questions, and there's a microphone. I saw it. I can't see it with the light on. There it is. There's a microphone there. There is a microphone there. And I believe there are people watching online, and if they pose questions, and if Raph likes the question, we can read it off of this board down here. So let's see. I think I'll let Raph take over.
Hi, thank you so much for the insightful talk. So I also work with the drones. So I wanted to ask, how do you approach to make the systems reliable and work 100% of the time? So like, what's the approach to do that?
Yeah, I mean, there isn't any one single thing, right? So the wonderful thing about robotics is that it's not just hardware, it's not just software, it's everything. It's system architecture, it's design, and reliability at the end of the day is, you're as strong as the weakest link. So yes, hardware is important, making sure that you have the right components. Connectors, make sure you pick the right connectors. I'm sure anybody here that's done robotics knows that crappy connectors are a bane to our existence. But that's a very, very small piece of it. It's making sure that you have the right system architecture, the right flow of information, you have the right compute doing the right things. Verity, we're a cloud-based solution. We do a lot of our compute on the cloud, but not all of it, because actually cloud is expensive. You want to do as much computing as you can on the edge. So it's figuring out what that trade-off is. And then using the right algorithms. What are the right algorithms to make your drones fly? At first, we very quickly determined that we had to spend years creating a system that was as robust as what we were able to deploy in 2021. So that takes a certain amount of patience to create a system that's that robust. And we were fortunate we were able to bootstrap our previous system in order to do that. So I think it's taking steps and finding the right investors that are patient enough to see you through that journey.
Thank you so much.
What was the hardest thing you did for your companies, and what did you learn from that?
Geez, the hardest thing that I did for my companies, I would say surviving COVID was hard, right? We actually came out of that much stronger. And what did I learn from it? I mean, I think I'm an optimist, right? No matter what's thrown at me, I always think that tomorrow is going to be a better day. I think what I've learned is just to have that attitude, right? That as long as you have a good group of people working with you, you can overcome any hurdle. I think the other thing that you learn as an entrepreneur doing companies is to be really brutally honest with yourself, right? When things are going well, celebrate it. When things are not going well, embrace that and fix it.
Hello, great talk. Heather Knight, Oregon State University. I really admire some of the recent work you've been doing with performers, and I was curious how you integrate choreography into these systems, and any tips and tricks for entertainment in general with robots.
Yeah, that's a great question. One of the really interesting things about entertainment is that it's actually the opposite of what you would think. You would think that there's a lot of spontaneity, but actually they want, like I was just at Eurovision. My goodness, they had 26 acts in a little over 2.5 hours. Everything is like clockwork. So they love determinism. Entertainment and live events love determinism. So at first, when we came up with our Lucy system, the choreographies are canned. They can't be changed. That was actually a plus for the folks we were working with because they want everything to be in clockwork. Now, for more experimental things like the dance troupe that we worked with from Australia, they wanted these things to have a little bit more character. And we've been contacted multiple times on making our systems interactive. I think that's a phenomenal thing to do. The problem is that Verity is a company that is a commercial entity and has to make money. And unfortunately, there isn't enough budget to be able to do these exploratory things. The Lucy in the Sky, the ones with the Australian troupe, it was actually everything was canned, right? Everything was created ahead of time, even pulling the Lucy back and letting it go. That's just the natural behavior of the system. So it's more with the artists working with the system the way it is and trying to get the most out of it. So I think the big lesson is, we have a lot of folks that come to us and say, we have this vision of what we want to do with drones. That never works, right? What really works is when it's collaborative, when the artists come to us, like the Australian dance troupe, and we work within the medium and we figure out what can we do together to bring the best out. So I would say that's probably the biggest lesson.
Thank you.
Hey, Raf, we have a question from online. I could read you from Mohammed Elnor. What challenges do you foresee in achieving real-time decision-making capabilities for drones operating in warehouses.
What was the first part again? There's all these qualifiers. I lost the first part. Can I see this without my glasses? Let's see.
I can read it again. Shall I read it again?
What challenges do you foresee in achieving real-time decision-making? Okay. Real-time decision-making. That is a great question. Of course, we do already a lot of time decision-making with the drones. They have to decide, how to navigate in the warehouse. But I think, the gentleman, he's talking about real-time decision-making as to when you notice something, how do you take action? Like for security, right? If you have security applications, you can't collect data, go to the chargers, process it, upload it to the cloud. That's actually one of the luxuries that we have with our current use case of our system. If you're doing something like security, then you need to react in real time. I think some of the challenges there are, where do you make those decisions? You should definitely do it on the device itself as much as you can, but sometimes you can't do that. So then communication needs to be a solved problem. Right now in these warehouses, there is very little connectivity. When we're flying, we don't need connectivity when we're flying. The only place we need connectivity is at the chargers, and in some warehouses, we don't even have Wi-Fi. We have to run an Ethernet cable to be able to download all the information we have once we land. But if you want to do real-time decision-making in these warehouses, you do need connectivity. And a lot of these places don't have it, so there has to be that infrastructure that you need, and you have to have the right architecture where you can make as many decisions as possible on the drones themselves. Fortunately, they already have quite a bit of compute power in order to do that, but you want to do some of that in the cloud, and figuring out what to do where, I think, is a challenge.
Hello, thank you for the talk. I had a question about more how you approached the business building side of Verity. If you had any insights on that, specifically how you built your technical team.
So I've been fortunate that with all the companies that I've founded, I've done it with other people. I think being a sole founder is a very lonely thing, right? So I've been fortunate with Kiva, it was Mick and Pete. With Verity, it's Marcus and Marcus. I also founded another company with some folks called RoboGlobal, but it's more in the financial services. And I think there it's really about, I think 3 is a nice number. Pick them very carefully. Make sure that you can laugh and joke with them. That's the most important thing. If you can't sit and joke with your co-founders, you've picked the wrong co-founders, right? You want to be able to share those moments. Pick folks that have different skill sets, but also have enough overlap, right? One of the reasons why Kiva worked so well is that all 3 of us were engineers. Mick and Pete, undergrad degrees from MIT, and Pete went on to be a professor at NC State. I was a professor at Cornell. Mick went into the business world, but we had that common experience that tied us together, and of course we love to joke around together. And I think it was the same. It's the same with thing with Verity. So I would say make sure you have enough overlap. Make sure that you have at least one other founder. 3, I think, is a nice number, and make sure that you complement each other.
Thank you.
Hello, thank you so much for your talk. I am Leticia I'm a master in Brazil, and we are starting a research about using drones for inspections. So based on the future uses, how do you see the future for drones?
So everything that I talked about, first of all, I should say, is indoors. Right from day one, we really focused on flying indoors. And there, if I look at the technology roadmap, if you think of sensors, compute, batteries, sensors are getting smaller, they're lightweight, low power, batteries are getting more efficient, higher density, compute is being tailored for embedded systems. I really do believe that in 5 years, we'll basically have flying mobile phones, right? So something extremely powerful that you can collect data anytime, anywhere, with a huge amount of compute that you can bring to bear on the device. So I think for indoors, that is the future. Part of it will be on the edge, on the device. Part of it will be on the cloud. I think for outdoors, it's different challenges there, right? There's a limit to how small you can make these things, right? Because you have to deal with the elements, the wind, the rain, everything else. So I think there's a limit to how small you can make these things, which inherently puts a limit on how inexpensive you can make these things. But I do believe that collecting data is the sweet spot for a drone. right? It's not efficient to use a drone to deliver a pizza. Okay? That does not make sense unless you want to pay a lot for your pizza. Okay? So collecting data, I think there's a bright future for that, simply because sensors are getting smaller, lighter, and perfect match for a drone.
Hey, thanks. Prashant Doshi from University of Georgia. So my question is really about how did you land on this inventory tracking problem? So like what kind of customer discovery did you do, and how did you figure out that this could be a problem that you could solve and that investors would be interested in this problem?
Yeah, I mean, we looked at this when we founded the company. There was a whole bunch of things that we looked at, right? And this was one of them. And we explored many of them, including live events, which really took off, and we did a lot of business with that. But this was also something else that we did, and the best way to see if there's an appetite is to actually work with real clients and see, if they see this as being valuable. And we validated in 2016. And that's what we came to realize, hey, there's a big opportunity here. And, then you have to convince investors, but hopefully you've done your homework by then and show that there's a real need there. With Kiva, we were very fortunate with our first client, which was Staples, right? That they had the faith to adopt a system like this, which really seemed like science fiction. We were also very fortunate with Verity that we had IKEA and DSV as our first clients. So a lot of times it's also having the luck of finding progressive companies that take the time to learn about you and what you're capable of and give you a chance.
Hi, Raf. Great talk. You mentioned that IMUs and battery technology were enablers for drone technology. These days we're seeing acceleration in compute due to all the deep learning rush that is happening. What problems are you excited that could be solved with these technologies in the near future in robotics? And if you have any other opinions about other technologies that are happening that are going to be enablers for robotics, what is your opinion about this?
Yeah, that's always a tough question, because you never know what, you can come up with 100 use cases and only a couple of them pan out. I mean, I'm going to be not very sort of visionary here and just say what excites me is this vision of having a flying mobile phone. I think all the technology is moving in the direction of having something there. And the fact that all of this miniaturization will allow us to basically sense almost anything. People are developing electronic noses. So being able to, put that on a drone, right? Radiation, right? So that you can infer if there's, a potentially illegal cargo in a warehouse, in a port. I think sensing is really exciting to me. It seems like everything is going in that direction. Small, lightweight, low power, better compute. I already said this earlier. People are really developing compute platforms for robotics, which will simply just allow them to be more efficient. Less of an issue with drones because you're going to need a certain amount of power just to stay up in the air. So, right now, the fact that we have efficient compute is not that, low power compute is not that big of an issue, but surely there's going to be a lot of other applications where that matters.
Thank you.
Hi, quick question regarding what you said about the mission planning. So in the warehouses, I believe you said the drones need to land to be able to receive the next command or the next plan. Do you believe that over time the optimal solution would be to have the drones act as a FANET to be able to communicate to each other so they can send the control signal, like the next mission plan, without having to land?
Yeah, so we can do that now. But the reality of it is that, as I alluded to earlier, a lot of these warehouses, their connectivity is really poor. So you want to come up with a way of operating so that if there is no connectivity, you can still do your work. And right now, we can do that. We don't need connectivity, so we can land back on the charger. Now, if you do have connectivity, then yes, you can actually send the information back earlier. You can process it while you fly, or you can receive new commands. So the system is architected in that way, but frankly, I said this earlier too, about performance versus reliability. Right now, we're not at the stage where we're really chasing the last bits of performance. Yes, we could probably do it more efficiently if we did that, but we're already providing so much value to our clients in this very monolithic, robust way of just going back to the charger, processing all that information, and uploading it to the cloud, that there really hasn't been a lot of pressure for us to do this. This would have been completely different with Kiva, of course. Kiva, we were constantly in contact with, with the traffic management system because that was central to be able to coordinate them.
Thank you.
You're welcome.
Thank you for your, oh, sorry.
Is that Tim?
Yeah, hey, Raph,
Hey,
how are you?
hey, Tim.
So you used the phrase first principles models about 15 times in your talk. Can you talk about how important it is to keep that in our engineering education in this age of learning?
Yeah, so was it really 15? How important is it? I mean, I think it is. There's so many things that we want to teach our students, and some stuff has to be left out. So I think it's important to expose people to the idea of first principle models. Do we need to go to the same level that we used to 20 years ago when we taught dynamics? Maybe not, right? But I think the core ideas of modeling a system and how we can use that to predict, I think that's something that should be pretty common. And of course, the people that specialize in certain areas of robotics and automation, well, they can double down on that while other folks don't. So I think that's my pragmatic answer to that. I would say, it's the same thing with, when I was an undergrad, we were taught complex variables in a lot of depth. And in some curricula, that's not even taught anymore, like conformal mappings and things of that sort. And it's a shame because it's beautiful, right? That math is beautiful, but of course it got dropped out because there isn't enough room. We're trying to cram too much into the curriculum. I think it's a real dilemma. What do we leave out? What do we put in?
Thank you for all your thoughts. I was just wondering, it seems like you have been very successful in getting people excited, not just about for investors in your business, but just everyday people about the technology. I was wondering if you have any lessons learned from not just garnering interest, but generating excitement on the technology that you're developing.
I mean, I think if you want to excite people, you have to be excited yourself, right? So I think I'm truly excited about the stuff that we do. I like creating. I like working with smart people. I think we're very fortunate, right, that we live in an environment where we can collaborate with, look around you, look at the people beside you, right? Look at their journeys to be able to get here. We're very fortunate that we get to hang out with these folks. So I would say, that excites me. That I feel very fortunate that I have the luxury to do this. When I fly in an airplane, it's a weird thing. American carriers, everybody closes their windows when they fly. I find that so strange. When I sit in a plane, I want to look out the window because to me it's a miracle that this thing is getting off the ground. Of course, I understand why it's getting off the ground, but it's still a miracle to me. So I think having this sense of wonder about the amazing things that we can do with this technology, I think that rubs off on other people.
Thank you.
So we've run out of time. Thanks everybody for being here. Let's thank Raf once again for that fantastic presentation. Good stuff.